When most people picture the solar system, they picture a flat diagram. 8 planets arranged in tidy rings around the sun, all sitting neatly on the same imaginary surface, like coins laid out on a tabletop. It is a useful image for teaching the orbital sequence. It is also, in almost every meaningful way, wrong. The solar system is not flat. It is not isolated. And the space above and below the plane where the planets travel is not empty. It is structured, layered, and stranger than most accounts of our cosmic neighborhood admit. To understand what lies in those directions, we first have to be honest about what the words above and below actually mean out here. Because in space, they mean nothing on their own. On Earth, direction is defined by gravity. Down is toward the center of the planet. Up is away from it. That logic is local and absolute in our daily experience, which is why it feels universal. It is not. An astronaut in orbit has no up or down except by choice of reference frame. 2 astronauts facing opposite directions are both correct simultaneously. When we talk about above and below the solar system, we are using the plane of the planets themselves as the reference, a convention, not a physical law. That plane is called the ecliptic, and it sits roughly aligned with the sun's equator. It is the floor of a room we defined ourselves. The planets orbit within a few degrees of that floor, most of them nearly flush with it. Mercury tilts about 7 degrees away from the ecliptic. Venus, about 3. The outer planets even less. Comets, by contrast, ignore the floor almost entirely. Many arrive from directions nearly perpendicular to the planetary plane, slicing through the solar system at steep angles as though the ecliptic were an obstacle they happen to cross rather than a structure they belong to. That observation turns out to be a clue about where comets come from. And following that clue is how we first mapped what surrounds us in every direction beyond the planets. The most remote structure associated with the solar system is also the least visible. The Oort Cloud, named for the Dutch astronomer Jan Oort, who proposed it in 1950, is not a disk like the asteroid belt or the Kuiper belt. It is a sphere, a vast, diffuse bubble of frozen bodies surrounding the entire solar system in every direction, extending from roughly 2,000 astronomical units out to perhaps 100,000. 1 astronomical unit being the distance from Earth to the Sun. At its outer edge, the Oort cloud reaches approximately 1/4 of the distance to the nearest star. It contains an estimated trillion individual objects, most of them small, frozen mixtures of water ice, ammonia, and methane. The leftover construction material from the solar system's formation, flung outward by gravitational interactions with Jupiter and Saturn in the early chaotic period 4.5 billion years ago. These objects now occupy enormous, slow orbits, some taking millions of years to complete a single circuit around the Sun. When gravitational nudges from passing stars or the galactic tide disturb them, they fall inward, appearing in our skies as long-period comets arriving from seemingly random directions. That randomness is the evidence. If these comets came from a flat disk like the Kuiper belt, they would arrive predominantly from within the ecliptic plane. They do not. They arrive from above, below, and every angle between. The source must be spherical. That is the Oort cloud. We have never imaged it directly. At those distances, individual objects are far too faint for current telescopes to detect. The cloud exists as a model supported by the distribution of the comets it periodically delivers, inferred from what arrives rather than from what we can see. Closer in, surrounding the solar system in a different sense, is a structure we have actually touched. Voyager 1 crossed into it in 2012. Voyager 2 in 2018. The heliosphere is the region carved out by the solar wind, a continuous stream of charged particles flowing outward from the sun in every direction. As this wind pushes against the interstellar medium, the diffuse gas and dust that fills the space between stars, it inflates a bubble around the entire solar system. The boundary where the solar wind finally loses its dominance to interstellar pressure is called the heliopause. Beyond it lies interstellar space proper. The heliosphere is not a sphere. The sun moves through the galaxy at roughly 828,000 kilometers per hour, and that motion compresses the heliosphere on the leading side and stretches it into a long tail on the trailing side. the same geometry as a raindrop falling through air. The solar system is not stationary in any sense. It is moving, and its cocoon of solar wind is shaped by that movement. Outside the heliosphere, the solar system is currently passing through what astronomers call the local interstellar cloud, a region of slightly elevated gas and dust density that the sun has been traveling through for tens of thousands of years. Beyond that sits a stranger feature still, the local bubble, a region roughly 1,000 light-years across that is anomalously empty. Almost no gas, almost no dust. Walls of denser material at its edges where the missing matter piled up. The current leading explanation is a sequence of supernova explosions that occurred in this region millions of years ago. Each blast swept the surrounding interstellar medium outward, excavating the cavity we now inhabit. We live inside the aftermath of ancient stellar deaths, a room with walls made of the debris those explosions left behind. And if we pull back further still, further than the local bubble, further than any structure associated with the solar system directly, we find that the Milky Way itself follows the same logic. The galaxy is not a perfect flat disk. Its outer edges warp and curve, bending above and below the central plane in a shape astronomers describe as a corrugated wave. Surrounding the disk is the galactic halo, a vast, roughly spherical region extending tens of thousands of light-years in every direction, populated by ancient globular clusters, isolated old stars, and what appears to be a significant quantity of dark matter. The pattern repeats at every scale. Disks embedded in spheres, planes surrounded by halos, flat structures wrapped in something larger and more diffuse. The solar system is not an exception to that pattern. It is an example of it. None of this shows up in the standard image of the solar system. The flat diagram with 8 planets and clean orbital rings is silent on the Oort Cloud, the heliosphere, the local bubble, and the galactic context that shapes all of it. That silence is understandable as a teaching tool, but it leaves most people with a mental model of where we live that is genuinely incomplete. The solar system is not a tabletop arrangement floating in a void. It is a layered structure surrounded by concentric shells of influence. The planetary disk, the Kuiper belt, the heliosphere, the Oort cloud, the local interstellar cloud, the walls of the local bubble, each one extending further, each one less understood. The directions above and below the planetary plane are not empty. They are, in a very literal sense, where most of the solar system actually is. We have spent most of human history looking sideways, planet to planet, orbit to orbit. The next era of solar system science is increasingly looking perpendicular to that plane, outward in every direction, mapping the full three-dimensional structure of the system we live in rather than just the thin disk where the planets happen to travel. The solar system is not smaller than we thought. It is much, much larger. And we are only beginning to understand its shape.